Reaction mechanisms. This is the second part of our chapter on collision theory. If you remember from collision theory, there were a couple of things that have to occur before a reaction can occur. One of these things is that the molecules need to collide either with the wall of the chamber or wall of the container, or they need to collide with themselves. Bearing that in mind, let's take a look at a balanced chemical equation we've seen before from grade 9. It's the respiration equation. So one molecule of glucose is going to react with 6 molecules of oxygen to produce 6 CO2, 6 H2O, and our ATP. Now, if we think about this in terms of collision theory, we need 1 molecule of glucose to collide with 6 molecules of oxygen at exactly the right moment with exactly the right collision geometry. Highly unlikely. When we look at reactions, a single molecule bouncing against the wall of a chamber, likely. 2 molecules colliding with one another with the correct collision geometry, a little bit less likely, but still pretty good odds. 3 molecules colliding with one another with the correct collision geometry, still possible. But when we get to trying to get 7 molecules to collide with one another at exactly the same time with the correct collision geometry, it's not going to happen very often. So once again, this is an overall chemical equation. If you click on the McGraw-Hill website below, you'll see what really happens with that glucose molecule. The glucose molecule becomes 2 molecules of pyruvic acid. Each one of those molecules of pyruvic acid then moves into a Krebs cycle, and within the Krebs cycle, it changes to make product at least 6 to 8 times, and then eventually you end up with your carbon dioxide, your water, and your ATP. So there is a reaction mechanism that occurs in many simple steps before we get to that add up to get to our overall equation. So reaction mechanisms, here are the key ideas. First of all, reaction mechanisms occur because of the collision of molecules or particles. Secondly, these collisions have to be simple collisions, so no more than 2 or 3 particles can be involved. 4 or 5, not likely going to happen. Next step, those chemical reactions occur as a sequence of elementary steps. So the simple collisions of no more than 3 particles and an overall reaction might be made up of maybe 3 or 4 elementary steps. And these elementary steps, as I just said, are known as your reaction mechanism, and they add up to your overall equation. So let's take a look at a simple real-life example. There's a 3-person job of raking leaves and taking them to the curb. So first job, rake the leaves into a pile. The second job is to put the leaves into a basket. And then the third job is to carry the leaves to the curb. First job requires the most time. Second job and third job will occur quite quickly. So if we were to use rate reaction terminology, we would say the first step happens to be your slow step, takes the most time. The second and third step happen quickly, so we call it the fast step. So let's take a look at an equation. We've got 4HBr reacting with a molecule of O2 to produce water and bromine gas. From the overall reaction, let me just grab a pen here. You can see that it's not an elementary or simple reaction. You've got 5 molecules in your overall equation. 5 molecules colliding at the same time is not going to be very likely. However, your reaction mechanisms are related to your rate law. If we look at our rate law, we found out that our exponents are the following. And because your rate law determines how quickly a reaction occurs, and if we think about it, the slow step of a reaction will determine how quickly a reaction occurs. Right? You can only move as fast as your slowest step. Another analogy, a chain is only as strong as its weakest link. So let's look at this reaction. A couple of rules we're going to have to follow. First of all, your rate law exponents, so the m and the n, have to be the same as the coefficients of the reactants in the slow step. This is key. Each step needs to be elementary, and then these elementary steps need to add up to the overall equation. So I often start with the slow step just to get it out of the way. So my m and n values are 1 and 1 respectively. So the coefficients of HBr and O2 in my slow step also need to be 1 and 1 respectively. And here they are, right? A value of 1 and a value of 1. After I get my slow step out of the way, then I just need to build to my overall equation, just bearing in mind that each step can contain no more than 3 collisions. So let's say my second step, I'm going to take my intermediate molecule. So once again, this molecule here is an intermediate molecule. It's not going to exist for a long time, and it's going to be canceled out as we go along. This part here is probably the most difficult part for students to get a comprehension of, because they want to make a molecule that's real. It doesn't have to be real. We can just kind of make up a molecule as long as it balances. So there's one hydrogen, one bromine, and two oxygen. So I just kind of put all the reactant molecules together into one temporary product molecule called an intermediate. Then I take my intermediate, I'm going to react it with another HBr to make yet another intermediate molecule, and so on. If we look at my rules that I need to follow, each one of my subsequent steps are elementary. 2 molecules colliding, 2 molecules colliding, 2 molecules colliding. Now for the final step, I just have to make sure that these elementary steps add up to my overall equation. Well, I produced the temporary molecule HOOBr, and guess what? I used up that temporary intermediate molecule over here. So they cancel out. I don't need to worry about it anymore. I produced yet another intermediate molecule, and lo and behold, I used it up twice to get rid of it. So when we look at my sum total, when I add up everything, think of I've got 1, 2, 3, 4 HBRs, 1 oxygen, 2 waters, 2 bromines, and it adds up to my overall equation. And just to sum up, my first step just happened to be my slow step. It doesn't have to be the first step. In this case it is. And the other subsequent steps are my fast steps. So let's take a look at this again. This is something that may occur. To get a reaction mechanism correct, like experimentally correct, is much beyond the level of this course. What we are only looking at is, does your slow step match the coefficients of your rate law, and are the proposed steps elementary, and do they add up to the overall equation? So this is my first try at a reaction mechanism, but there's more than one possible answer. It could happen this way. Let's say my slow step is not my first step. I create my intermediate molecule. Now I get my slow step in here. I just highlighted it in blue, or just drew it in blue. Then I've got my other reactions. And so long as it adds up to my overall equation, I'm okay. Well, let's take a look. Here is my intermediate, and here I cancel out my intermediate. Here is yet another intermediate, and I get rid of it over here. And then a final intermediate over here, and it gets used as a reactant over here. And when I add everything up, I end up with my overall equation. And once again, just to use the terminology, my first step is my fast step, my second step is the slow, and the other ones are the fast. Right? Key thing, make sure those coefficients of your slow step match the rate law. So the rate law and your mechanism are related to one another. Now, oftentimes in your textbook, you might see letters used as molecules. So as the example here. So the reactant is A and B, the product is C and D. And this is sometimes confusing to students as well. Once again, let's say we found the rate law by experiment, and these are my exponents over here. So my slow step, I know, has to have a coefficient of 2 in front of the A and a coefficient of 1 in front of the B. And I'm going to make up some intermediate molecules as well, but I'm not going to use the AB. I could. I'm just going to use different letters just to show you a different variation. Once again, I said I start off with my slow step just because I find it easier. You don't have to. And then I'm going to do a series of elementary fast steps. And you'll note that my intermediate here, I used a different letter E. And that's fine so long as I cancel out that E, because E does not appear anywhere in my overall equation. And also note how many molecules are involved in this elementary step. If you said 3, you're correct. There are 2 A molecules and 1 B molecule for a total of 3 molecules colliding. Yes, there are only 2 reactants, but there's 2 A's and 1 B for a total of 3 molecules, so we're at the max of an elementary step in terms of the number of molecules involved. And so when we look at this here, I have my temporary molecule E, intermediate, cancels out. Another intermediate F gets canceled out. Another intermediate G got canceled out. And then I'm left with my overall equation. So if we look at this in terms of an activation energy diagram for a two-step mechanism, we looked at energy level diagrams before for a single step. So we've got my overall equation. We see that there are 2 bumps on there, so this must be a two-step mechanism. Transition state, very temporary molecule, but not the same as an intermediate. Your intermediates are found over here. So a transition is different than an intermediate. So step 1 and step 2. Which step is your slow step? Slow step is the one that's going to have the highest activation energy. So take a look at your 2 activation energies, EA1, and over here we have EA2. Right? The activation energy of your second step is classified as the fast one because it's much smaller than the activation energy of your first step. Now, what happens when we add a catalyst to a reaction? Well, the catalyst can behave in a couple of different ways. If it's a nice elementary reaction and it's a type of catalyst that simply lowers the activation energy to make things work faster, the variation in the diagram is over here in figure 1. But a catalyst can act in a different way. It can actually change the mechanism of the reaction. So over here in figure 2, without a catalyst, this is a nice single-step reaction. But if we add a catalyst, we change the mechanism. Now it becomes a 1, 2, 3, 4-step reaction. But when we look at the activation energy of the 4 steps, it's still smaller than the activation energy of your no catalyst reaction. Now, one little kind of clarification here. I don't like the way they did the EA with the catalyst. We should talk about the activation energy for each individual step. So for the first step, I'm just going to change colors of the pen here. So let's go with a nice blue. So the EA for the first step is right here. The EA of the second step, well, it comes from where you start off to the bump. So the EA of the second step is over here. The EA of the third step is over here. And the EA of the last step, let's say, is right here. So if you look at it, 4 different steps, and I believe the largest activation energy is over here. So this would represent your slow step. And that's the reaction mechanisms.